This program is brought to you by Stanford University.
Right. Well, welcome. I'm going to talk to you about a topic that has been a great interest of mine and many other folks in the Aeroastro department and around the country and around the world for many years. And this is the impact of aviation on the environment and what we call sustainable aviation and what we're looking at for the future of air transportation. I'm going to tell you a little bit about aircraft fuel efficiency and a high-level look at the effects of aviation on the global environment. And then tell you a little bit about an initiative in the Aeroastro department aimed at addressing some of the problems with aviation and the environment. That's a high-level overview. Then I want to talk a little bit about some of the technical work that's going on, discussing future aircraft and the possibilities for the next 20, 30, 50 years in terms of designing airplanes for minimum environmental impact, which requires modeling that impact, looking at what we get when we do that, and then talking about some of the new technology concepts that are particularly promising. Feel free to interrupt me. Just raise your hand. I'll try to leave some time at the end, but go ahead. Yes, please.
Do you provide your slides? This is my first time afterwards for us?
Yes, you'll be able to see these. There are actually going to be a couple that are removed because they have been done by people who don't want them posted on the internet, but they will be available. Okay. This is a plot that the air transportation industry likes to show dealing with aircraft fuel efficiency. And they like to show this because it's a tremendous success story in many ways. Back in the 1950s, the first jets here used a great deal of fuel. This is a plot versus year, actually initial service year, of the relative fuel use per seat kilometer, per number of seats times the distance flown. So it's like miles per gallon divided by passengers, right? But current airplanes use something on the order of 70% less fuel than the very first jets. It's a tremendous advance. I have to say this is partly because the first jets were so bad. And if you actually compare these two, it's still 50, 60%. So it's still really, honestly, a real success story in terms of the efficiency of aircraft. The next generation of airplanes, 787, A350, et cetera, look to save another 20% or so over today's fleet. And one of the troubles with this is that people cite improvements in efficiency of about somewhere between 1% and 2% per year. Clearly, if we've gone 50% or more over the first 50 years, we're not going to do another 50% in engine efficiency over the next 50 years. Can't do more than 100% efficient on engine technology. So what that means is that it gets harder and harder to make improvements, and this is one thing we're going to be talking about. Where we are now is pretty impressive, actually. This is a 737-800. It carries about 130 passengers. That's not full. It carries more than that. That's 80% load factor. It's 80% of the airplane's full, which is typical these days. It takes 29 gallons of fuel per person to fly across the country from Seattle to Washington, D.C. So that's 81 passenger miles per gallon in US units, right? That's pretty amazing. That's better than 2 people in my Mini, and it's 10 times faster. So very impressive story on the efficiency of air transportation. We're going to be talking about commercial air transportation, not private airplanes or personal air vehicles, because commercial air transportation has the biggest effect on the environment. So that's a great story. but transportation's contribution to greenhouse gases here in 2004 is about 13% of the total. This is human-generated carbon emissions. Actually, this is actually greenhouse gases. This is CO2 emissions. Aviation is about 13% of that. Okay, so it sounds like 2 to 3% of carbon emissions are associated with air transportation. However, it's a more complicated story than that. And as you'll see, the impact of aviation is actually dramatically larger than that, and in the future, dramatically larger yet. What's going on is that the engines are burning kerosene, conventional petroleum-based fuels. In fact, the transportation sector uses by far the most petroleum fuels of any sector in the energy consumption. But airplanes burn kerosene-like fuels and emit carbon dioxide, just like everything else that burns hydrocarbon fuels. Interestingly enough, because it's soaking in oxygen from the atmosphere, for every kilogram of fuel you burn on an airplane, you put in 3 kilograms of carbon dioxide. This is true of all kinds of hydrocarbon combustion systems, right? So you think about that, that 29 gallons, which is something like 30 times 6, 200 some pounds of fuel that you burned on that one very efficient trip across the country, still creates 3 times that. We're starting to get a good fraction of a ton in carbon dioxide. One of the troubles is that in addition to carbon dioxide emissions here, airplanes, like many other things that burn hydrocarbons, produce nitrogen oxides, water vapor, sulfur oxides, unburned hydrocarbons, soot, and things that you wouldn't think are problems, like it's just producing water vapor, turn out to be problems when you deposit them at 40,000 feet. And so we'll look at that a little bit. But we have to look then at both the carbon emissions as well as the non-carbon emissions and its net effect on the environment. One of the reasons that it's not just a story of CO2 is indeed that there are these other species, but also that the altitude effect is quite important. This is a plot from a study of hydrogen-powered airplanes. And what you see here is the relative climate effect for NOx, water vapor, and carbon dioxide at different altitudes, ranging from 5 kilometers up to 12 kilometers. Airplanes are operating usually in this upper region. What you see is that at low altitudes, hydrogen, the effect of hydrogen is very small if we were burning hydrogen. But at 12 kilometers, in fact, it has a similar impact to burning kerosene at low altitudes, even hydrogen burning. Kerosene here is substantially greater than hydrogen, but the contribution of different species to climate change really does depend a great deal on altitude. So that makes the analysis of this a little bit difficult. What all this means, you could go online. This is a carbon footprint calculator from BP. Air France has another one of these. Most of the airlines have them now so that you can go and figure out just how much your flight is going to contribute in carbon dioxide, and you can then pay a company to offset these or just feel bad or something. But here's what this means. If you assume that you have a family of 4, take 2 long-distance trips a year, have 1 family car, you find that the amount of carbon emissions associated with air transport is similar to the entire year's household energy use, similar to all of the use of the car. The climate effect can be quite a bit higher. So another number here, fly to Paris from San Francisco for 1, that's about 15% of the average household energy use, 1 trip. So it is one thing that we do that has a big effect on greenhouse gas production and climate change. What this means, by the way, this is a plot of the carbon emissions from global aviation and several countries. So aviation produces about the same amount of carbon here as the entire UK or Canada, for example. Here's Japan, Germany, right? So it's not, although we're talking about 2% contribution, it's a significant thing, and we have to think about it, especially if we're in the business of building airplanes. It's actually far worse than that, and the reason it's far worse than that is because air travel is growing tremendously. It has for many, many years, even with dips associated with 2001 events. We are now actually still on this track. No one, of course, can predict this, and especially with global economy changes, we don't know this will happen, but historically, there's been a very significant, something on the order of 5 to 6% growth. In Asia, it's more than that. And so if you extrapolate, it doesn't take too long until you're talking about doubling and tripling the number of those passenger kilometers that are flown every year. And that means the total contribution is going up no matter what you do, or you have to do a lot to make it not go up a lot. So this has led to people being very concerned with the impact of global aviation. This is a thing from CNN that, among other things, says, aviation, the fastest growing source of greenhouse gases. That's surely not true, and doesn't really mean much, but with radiative forcing factored in, aviation represents 12 to 13% of emissions. Well, that's also a lot of things that are a little bit tricky in looking at statistics, but the point here is that people are becoming aware of the impact of aviation on the environment and becoming concerned about it. Yes?
By emissions, are they referring to total greenhouse gas warming effect?
Who knows what they are referring to. We'll see some numbers here in a minute so you can get an idea of what we really think that is. So the problem here is that if you really anticipate a threefold increase in global air travel over the next few decades, we're going to have many problems. And one of them is certainly going to be the environmental impact. There are also going to be issues with safety and capacity and many other things. And so we are very concerned about all of these things and being able to maintain the ability to travel as we do now. This has led to a number of new initiatives at the government level. Both US, the FAA is doing things, NASA is doing things. In Europe, there's a Clean Skies initiative, which is putting in something on the order of $2 billion over the next 7 years to address exactly these issues. So these are just starting up, and one of the initiatives that's starting up is some work in the Aeroastro department with the goal of developing technologies that will allow us to accommodate this growth and allow the tripling of capacity without an enormous increase in environmental impact. So what we'd like to do is allow a tripling of capacity with an actual reduction in environmental impact. So this is a plot of the expected traffic, the fuel usage, assuming a certain amount of improvement in aircraft, and what we'd like to do to have the emissions level off here so that in 2030, 2040, we are not doing any worse than we are now. This is what we mean by sustainable aviation. We'd like to be able to continue adapting to world growth without making a situation where we simply can't sustain that environmentally. This particular initiative involves a variety of research thrusts. One of them looking at new concepts and technologies that can help achieve this, and that's really what I'm going to be talking about today. But in AeroAstro, we also have folks working on airspace systems, how you deal with the complex system of aircraft in the airspace, and also monitoring the system at a larger scale. So one of the research thrusts that I won't say much about has to do with actively monitoring and managing the system, and in particular the environmental footprint, so that you can control the operations to reduce the impact. One example of this might be real-time monitoring of winds and conditions around an airport to try to reduce the noise footprint. Another might be to actively monitor the conditions in the atmosphere that cause contrails. By actively monitoring, I mean using satellites and a variety of inputs so that you can tell an airplane in real time, look, there's an area that's going to cause contrail formation, replan your route, change altitude, do something, because contrails, as we'll see, have the potential of causing climate change as well as along with the CO2 emissions. And here you see contrails formed in the supersaturated air. But the conditions for contrail formation are actually pretty specific. That is, you change the altitude by a few thousand feet and you won't produce contrails. So knowing that that's going on, we can make a big difference. And here you see some contrails. This is Florida. Right? So this is southeastern US. Fair fraction of that area is covered by contrails, and this has an effect on the balance of radiation from the sun and emissions from the Earth. We would also like to be able to use things such as precision navigation to reduce the environmental footprint. This is a plot of the tracks of airplanes departing from Atlanta. And this is a plot of what could be done, and this is an actual demonstration, what could be done using precision navigation systems and GPS to not just say, okay, turn right now, but rather to follow a path that's pre-planned, a four-dimensional path. And you can see that the tracks of the airplanes are much more restrictive, and therefore the noise impact on the community is much reduced. We'd like to use these technologies to improve capacity, reduce environmental impact, and increase safety. To get a feeling for really what we're talking about here, here is a movie of actual positions of airplanes over the US in a day. We're looking now at 1,700 airplanes. Now it's the middle of the night, so things get pretty quiet. And then you'll see as the sun starts rising in the east, we start getting more traffic in the east. And then as it moves west, we now have 4,000 airplanes flying. And this is a real challenge to try to manage in any reasonable way. Certainly, there are opportunities there to do more than we're doing now. So let me say a little bit about what we envision doing in the future, looking at aircraft technologies where we design the airplanes not to just minimize cost, but to look at their impact on the environment. I'm going to talk about three things: how we model that impact on the environment, show you some results, and talk about some new ideas. So at Stanford, we developed methods for designing airplanes and evaluating them that include not only their performance and stability and control, structures models, economic models, noise models, propulsion, all that communicate with the database. This is a complex multidisciplinary design problem. We use numerical optimization to vary all kinds of parameters about how the airplanes fly or what they look like, and then come up with, in some sense, the best design subject to whatever constraints that we've imposed. One of the things that we've done with this analysis tool that we also use in classes here is to develop improved models for climate impact and to include that in the entire aircraft design process, right from the very beginning. That is not so easy because there's a lot going on. This is a simplified version of a famous chart from the IPCC, the International Panel on Climate Change, that looked at the aviation impacts on the environment. And what you're seeing here is the so-called radiative forcing. It's the imbalance in energy flux or power flux between sunlight and reflected and other fluxes. And what we see here is the delta due to aviation actually over the history of aviation. And so what you see here is CO2 producing a net radiative forcing that's shown by the height of this bar, with this being an uncertainty in the estimate. Here you see ozone and methane, which are affected by the presence of NOx, nitrogen oxides. Nitrogen oxides tend to deplete methane, but create ozone. And the extent to which they do this depends on lots of things. Water vapor, sulfates, soot, contrails, cirrus clouds. What you notice here in the contrails and cirrus clouds is that the effect is not trivial, but the uncertainty is huge. And so we have to think about what that means. So here's the total radiative forcing. So if we're going to develop a climate model for airplanes, we have to look at the effect of many of these things. We're going to ignore a few of these small ones, but many of these things whose impact is actually pretty hard to figure out, because radiative forcing is a pretty bad measure of climate impact. Just as an example, CO2 can stay around in the atmosphere for 50 to 100 years, whereas contrails disappear in a day or less. And so to properly include these in some kind of model is a challenge. So radiative forcing has some difficulties. The effects differ due to different time scales. Different sources produce different surface temperature changes. It's not a great model. We're going to use something else that's a little more sophisticated that is going to be used just for our purposes. Let me show you what that is. We are going to use some kind of estimate of temperature change over a 100-year period due to the presence of these emissions deposited at different altitudes that you see here. It's particularly challenging because the non-CO2 emissions are very altitude dependent. This is the effect of NOx emissions and CO2 emissions, NOx emissions and contrails, which vary quite a bit with altitude. We are not trying to estimate exactly how many degrees change we expect in 100 years due to this, fortunately. We are not, like some other people, challenged with the task of trying to make policy based on this. So we really only are going to be using this to compare different airplanes. And so we don't really care what the exact numbers are, but we want the effects of the different species and the different airplane parameters to be captured properly. So we're looking at contrail formation, NOx effects on ozone and methane. And we take the emissions, we estimate the radiative forcing. In this step, are able to account for the time variation of short-lived emissions. These are based on climate models from real atmospheric scientists, not airplane designers. And we've developed a simple version that measures this change in temperature associated with a 100-year operation of this system over the time. This just shows some example results of, this is the CO2 radiative forcing. This is the radiative forcing due to contrails, and this is the time dependence of both of these. Actually, this is carbon dioxide in blue, contrails in the dotted line, and here we're looking at radiative forcing versus the new metric, a global temperature change. And you could see their time dependence is quite different, and therefore you end up with different conclusions. So let's take a look at what some of those conclusions might be. We'll take a look at applying this model, doing optimization for future aircraft designs, and seeing what we get. So here's the problem. We're going to design a 162-passenger airplane. This is roughly in the class of airplanes that people are interested right now, which is going to replace the vast majority of airplanes flying. It's going to fly 3,000 miles, and it's going to look a little bit like a narrow-body airplane, like a 757 or a 737. Not going to be some big, yeah. Jeff doesn't like flying in 757s. Neither do I. So we have something for you in just a minute. We're going to fix the fuselage. We're just going to say we're going to keep the passengers just as uncomfortable as they are today, but we're going to reduce their guilt, so their environmental impact. We're going to change lots of things and constrain the airplane. So we have 16 design variables, like the size of the wing and what the span of the wing is, how fast the airplane flies and at what altitude, how big the engines are, this sort of thing. We're going to make sure all these airplanes take off and land on the same runways, are stable, and fly the same distance. We are going to look at the difference between these airplanes if we try to minimize cost, minimize fuel burn, minimize NOx emissions, or minimize the complete 100-year global warming estimate. And so here are just some examples of what you get for these cases. This is a scaled measure of cost, fuel burn, NOx, and CO2 NOx, and the contribution to global warming for an airplane that's designed for a minimum cost. Okay? So all of them are 1 for this baseline airplane designed for a minimum cost, and in fact would meet the environmental regulations of today. If we minimize fuel burn, we can actually do quite a bit better in reducing the amount of fuel that's used and have some impact on global warming here. If we minimize NOx, we can have a much bigger effect on NOx. And if we actually look at minimizing this climate impact, we have actually a very big effect here on that metric. We don't really want to look at any of these airplanes because an airplane designed to minimize climate impact with no thought for cost is going to be a pretty silly design. It's not practical, and in fact, you can see that by looking at what happens to this airplane. This airplane ends up flying at a little more than half the speed of existing airplanes. That's a big problem. And so what we really want to do is to look at all of these metrics at the same time. And this is called multi-objective optimization, and there are new techniques for being able to do that. This is the minimum cost design, some specs on it. It flies at 0.85 Mach number, 85% of the speed of sound at 39,000 feet. The minimum fuel airplane flies at Mach 0.61, about the same altitude. Minimum NOx airplane is down to Mach 0.5, which is a big problem. And down to 0.45, this is pretty much half the speed of conventional airplanes. So we're not interested in that. Here's a multi-objective study. So here we're looking at 2 objectives. On the vertical axis, the climate impact, again, all reference to our baseline airplane designed for a minimum cost. And here's the cost. Okay? And so here's our minimum cost. This is our minimum climate change airplane. And you can see it costs 12% more. Although it saves lots of fuel, you have to pay the pilots more. Your total utilization of the airplane over the year is less. All of these things are included in the cost modeling. And so this is not an interesting airplane to look at. But the curve is very interesting because it says that you can actually make some difference without changing the operation of the airplane much. And then you can have an enormous impact on climate change by changing these airplanes before you start really slowing down. So in red is the Mach number, the flight Mach number. This says that by slowing down from Mach 0.85, which would be typical of a 777 or 767 maybe, slowing down to 0.75 or 0.71, you get most of the effect on the environment by doing that. And the cost change here is on the order of 1 to 2%. Everyone, not lots of us would pay 1 or 2% extra to reduce climate impact by 50, 70%, right? But it's a new airplane. By the way, 737s actually, the old 737s fly at this speed anyway. Okay, so one of the problems with this is that some of those big changes are associated with those species that have big uncertainties. So that included the effects of contrails and cirrus clouds, which frankly, we don't know very well. So what we'd like to do is look at the effect of uncertainty on those results, right? These kinds of things. And what we did, and when I say we, I actually mean Emily Schwartz, who's a PhD student in the Aeroastro department, looked at using 2/3 confidence intervals from this IPCC estimate and some other input to try to look at all those results that I showed with different models. And what you see, what we did was to take the low estimate in green here for NOx, contrails, and cirrus, high estimate for NOx, but low for contrails. So all different combinations of the different confidence intervals. And you get all of these curves having to do with the 100-year climate impact. One is where we started. And what you see is if you use the higher estimates than the mean, you get big increments in global warming for the existing airplanes, the minimum cost airplane. If you assume contrails and cirrus clouds don't do much, you get a pretty small effect here, much less than what we're predicting from the mean of the IPCC data. On the other hand, these are all the optimum airplanes, remember, all the way out here to the lowest climate impact case. And what we see is that regardless of our estimates, maybe we are high or low, but we can be down here to this level, which is something on the order of 25 to 30% of our mean estimate right now, regardless of those uncertainties. The total change may not be big if we were wrong about cirrus clouds and contrails, but it still might be a really good design. So, and again, at 2 to 3% cost increment. So, summarizing some of the results of that optimization study, only about 1/3 to 1/2, depending again on how important you think cirrus clouds are, of climate impact is associated with CO2. And that's one of the reasons why the 2% versus the 4% versus the 12% depends on what you're using there. We really don't know at this point. Designing an aircraft to have low fuel burn can create small changes in the climate change estimate if you operate them at the same altitudes and speeds we're talking about now. But if you allow them to slow down a little bit and come down some in altitude, you can have much larger effects. Uncertainty is important, and this is a big problem right now with the model. We've shown that it doesn't necessarily affect the conclusions about what you would do. Nonetheless, work is continuing by many people, including Professor Lele and Mark Jacobson here at Stanford on improving contrail modeling and its effects. So the last thing I wanted to talk about were some new ideas. If you weren't going to just design conventional airplanes but insert new technology, what could you do with all of this? First thing you could do is change the fuel. And there's a lot of interest and experimenting with biofuels and alternative fuels of one sort or other for transport operation by commercial carriers, here by Virgin Atlantic. We recently had a flight by Qantas that did the same thing, using different fuels. The Air Force did a demonstration of using gas-to-liquid technology. The Air Force was more interested in assuring that the fuels were there than necessarily reducing environmental impact, but still an alternative fuels look. One of the problems with alternative fuels for aircraft is that the constraints are different from what we think about when we think of alternative fuels for cars. Ethanol, for example, is a really bad fuel for airplanes, principally because its specific energy, the amount of energy per unit weight, is about 60% worse than what we use right now, Jet A. So your range would be dramatically reduced. The operational issues are tremendous. Whereas hydrogen, liquid hydrogen, is vastly better than what we use today. Unfortunately, liquid hydrogen has a very large volume, and even in liquid form, certainly compressed gas form does too. And the shielding required is high. So we would really have to redesign the airplane tremendously to be able to use hydrogen. And we'd also have to operate the airplane differently because, as you saw in that earlier slide, even hydrogen is not all goodness at high altitudes. Bottom line here is that hydrogen fuel is certainly not an obvious choice for airplanes. Biofuel in some form or other might be interesting, but just using ethanol certainly isn't. One thing that people are looking at are a variety of bio and other jet fuels that are synthesized so that you basically use these as sources of energy but go through a process that produces a synthetic kerosene that has the same kind of specific energy as Jet A. One can also use things like natural gas that has a lower carbon content and produce synthetic Jet A, which again has somewhat lower carbon emissions. There are other technologies that are really interesting. One of the problems with airplanes that are designed to fly to Sydney is that they have to be designed to fly to Sydney. If they fly to Sydney, they carry a tremendous amount of fuel on board, and they burn a lot of fuel just because they have to carry the fuel. And so more than that, more than the fact that you have to burn extra fuel to carry the fuel that you'll need for the second half of your flight, the airplane has to be designed to carry that fuel. All the extra weight in the structure and everything else is a penalty, a fuel burn penalty, for every 500-mile flight that airplane takes too. So people have proposed not designing airplanes to fly 9,000 nautical miles, but designing them to fly 3,000 nautical miles. And while people don't want to take multiple hops, maybe you could refuel them in flight. And in particular, there's a lot of work by the military in developing autonomous aerial refueling. You don't want the pilots paying attention to where the fuel hookup is while they're flying the airplane. But if it were all done autonomously, this represents an interesting possibility. People have done analysis of that and produce estimates of fuel savings for long flights that range from 20, 30, even 40%. So could be a big impact. Another thing that we're interested in particular is flying airplanes in formation. Now, this is a lot of airplanes, but just 2 or 3 airplanes in formation you can take 3 200-foot span airplanes and have roughly the aerodynamic efficiency of a 600-foot span airplane, which you couldn't possibly build. And as you saw from all those optimization studies, That's one thing that characterized the lower environmental impact airplanes, bigger span. And yet, you can't park airplanes with 600-foot spans at SFO or anywhere else. So there are some interesting ideas there. NASA has done some work in actually demonstrating this. These are two F-18s flying in formation. This is what we estimate the change in range would be, depending on whether you have 1, 2, 3, or 4 airplanes. It's not 1 or 2%. It's a significant impact. This, again, would be done autonomously, so the pilots wouldn't have to be flying wingtip to wingtip. And in fact, these airplanes could be spaced apart hundreds of spans, a mile or so apart, so you're not flying like the Blue Angels in this case. Okay. The last thing that I'm going to mention is what you get if you just change the airplane completely. Here's a 787, which does not change the airplane completely. The new engines are about 8% better. The airplane, when you redesign it to take advantage of that 8%, is about 20% better, which is what we said at the very beginning of this talk. Much of this comes from the fact that the airplane doesn't have to carry the extra fuel that it would have had to carry if you didn't have the 8% better engines, and all of this gets recycled. But there's also some aerodynamic savings. There are lots of new technologies that we might take a look at. I'll show you some pictures real quickly. This is one of those Pareto fronts for conventional airplanes. Here we've assumed laminar flow on the wings, some new materials, and we go from this kind of trade-off front, in this case NOx versus fuel, so CO2 versus NOx. We go from this front to this one. We're talking about big changes once again. So here's an airplane that might, in fact, take advantage of that. This is an Airbus design, unswept wings, so they have slowed down a little bit. It has actually a strange structural technology, in this case with a strut to reduce the wing weight, to enable that larger span. A interesting horizontal tail which shields the people on the ground from engine noise. You could do, it has high bypass ratio engines, new engine technology as well. We could change the wing somewhat in a number of ways to reduce the drag of the wing. In fact, using some smart technology which senses when gusts come and reduce the loading on the wing to allow you to have a larger span without more wing weight. And this is some study that we did here on active load management for airplanes. We could put the tail in the front, which has some potential advantages. We could change things completely. This is a artist concept of a blended wing body design. It looks real, but this is a fictitious airplane in front of this fictitious city here. This is really what it looks like. It's a tailless design, and the passengers can sit in various arrangements that Boeing has done mock-ups of, and which are much more interesting than your 737. Okay, so to wrap up here, there's some large potential savings that are possible with designs that are really tailored for low noise, low emissions, and they require pretty limited cost and utility changes. Greater savings are possible when we start looking at new configurations and new technologies. These kinds of techniques of looking at multi-objective optimization with climate modeling are very important in doing conceptual design of these new ideas. We're continuing study of designing the complete system, that whole group of airplanes rather than just one airplane, looking at new configurations and improving the climate modeling. So to wrap up, I kept saying we, lots of folks in AeroAstro and elsewhere. Emily Schwartz did a lot of this work. Nick Antoine, a former PhD student now at Airbus, did some of that. Dave Daggett is from Boeing, who's done a lot of interesting work on alternative fuels. We're partnered with folks from MIT, Georgia Tech, and elsewhere looking at these things, and some of this work was particularly done by Karen Wilcox at MIT. Support from NASA, Langley, Boeing, NSF, and we're doing a lot of cooperative research. So I'm happy to answer some questions. Thanks. Yes?
On the capital cost versus fuel trade-off, doesn't a plane typically burn several times its purchase price in terms of cost of fuel, such that a 10% decrease in fuel would be worth a lot?
Yes, so the cost was not capital cost. It was actually a metric that was closely related to total operating cost. It included all the fuel costs, all the costs for the pilots, even the food that you eat and everything else. All of that was in that metric. In fact, what that metric really was the amount that they'd have to charge each passenger to fly that flight and still make 5% with a given load factor. So it included that effect, and even then, you see a big change in environmental impact with a small effect on cost. Yes?
Yeah, I had a question about the cost model too. What assumptions did you make about fuel, cost of fuel itself, and in particular, any recognition of the externality related to environment, climate change?
Yeah. So it's a very interesting question these days because the cost of fuel has varied so dramatically over the last year. In fact, probably the biggest impediment to this development is the falling cost of fuel. It may well have been that while people aren't motivated to spend billions of dollars in new airplane development for this uncertain climate impact, they certainly would with fuel at $5, $6 a gallon. So the numbers you saw there were for fuel at $2 a gallon, and there were no externalities built in there. So treat that just as a straight number that you would have to pay with no carbon taxes, no externalities at all, and use the other scale to judge what you think might make sense. I will tell you that taking proposed carbon taxes in Europe right now has very little effect on these costs. It would have to be much bigger. It would have to be large changes in fuel price. Yeah.
This just as a point of interest, flight from San Francisco to Johannesburg and back to offset is $89.
Right.
And so if every passenger paid $89, $90 more, presumably the airline would be offsetting the cost of the CO2 emissions. So it wasn't clear to me from the answer that you were actually factoring that in.
No, that is not factored in. It's today's operation.
What would be interesting would be to see what the monetized cost is. You're saying it's not big,
It's not significant.
but if it gets to $100, would that start being significant? If it's 20, maybe it's not. If it's 100, 20, by the way, was the price that was used.
So what did you pay for the entire ticket to South Africa?
Probably a lot more than that.
Right.
Why,
50,
20
10
times. Yeah. But I'm saying that they work on $20 a ton. If it's 100, I was just wondering how that changes things in terms of your analysis.
So it probably has a big effect on the market, and that's probably the biggest thing missing from this cost model. That is to say, if you tell people you could take this airplane and offset your carbon costs for $100, or you can take this airplane which flies 10% slower and has no impact or much less impact on the environment, what would you do? That modeling is not done. I don't think anyone's done that, and it would be an interesting trade. Yeah.
One dimension not discussed is the flight patterns. So my understanding is that if you fly to a point rather than say changing planes in the middle of the country, you save on CO2 and fuel because a lot of it's burned during takeoff and landing. However, economic incentives right now are that it's cheaper to actually get tickets to change planes once, twice, 3 times. A, is that true, and how significant is it? B, if it is, what can be done to actually change the flight patterns to be more efficient?
Yeah, so there are 2 kinds of changes in flight patterns that people talk about. One is just doing automatic rerouting to try to minimize fuel burn, for example. People were doing a lot of this when fuel prices were $4 a gallon. That is worth, if in an optimistic sense, maybe 4 or 5%. That means this includes not only making small deviations based on winds, but also minimizing flight delays and all of that. It's not a huge number, but it's not trivial either. By changing the way the airlines operate, people are doing studies of this, both here at Stanford and all over the world. One of the difficulties there is exactly what we were talking about earlier, the marketing, because if, in fact, you save the airplane burns less fuel by doing point-to-point rather than going through the hub, you have to say, yes, but how many people really wanted to go there versus, so how does that affect the load factor of the airplane? If you only have the airplane half full on several of the flights going point-to-point, but it's totally packed going between the hubs, it has a completely different effect on the environmental impact.
Could that be offset by having planes that are half the size, or is that inherently less efficient?
So they tend to be less efficient, but they also are limited by capacity. So if you immediately reduce the number of very large airplanes to all be regional jets, the noise level would actually go down at airports, but there's no way you could accommodate the existing capacity, which is actually pretty close to the limits of many large airports around the world. So it's a very tricky problem there, but it's an interesting problem that people are working on, combining system scheduling with airplane design and everything else. Yeah.
Capacity being total takeoffs and landings.
Right.
Not total passengers.
Exactly, right. In that case, it's limited by takeoffs and landings, right? Yes.
Some years ago, there was evidently a serious interest in the military for hydrogen-driven airplanes.
Mm-hmm.
Does that still exist?
In certain circles. So there are several programs that are intended to try to develop very long endurance drones, particularly for surveillance. You'd like these things to be kind of atmospheric satellites that sit up there all the time looking at some parts of the world so you know what's going on. And yet aren't 22,000 miles away and you can bring them back. But there are programs right now looking at versions of this that fly anywhere from 2 weeks at a time to 5 years at a time. And some of those are very interested in hydrogen fuel. The hydrogen fuel transports have been looked at as well, mostly to increase the range of the airplane. And so all of this is being done by places like Air Force Research Labs and contractors around. Still going on, but I have to say the serious application of this would be in high-altitude unmanned airplanes.
Well, I think at that time they were concerned with supersonic planes,
Mm-hmm.
and they were going to use titanium alloys
Yep.
for these. Some of these alloys were exactly the same materials that one uses to store hydrogen, which means they react with hydrogen, and the airplane would be in little pieces very quickly.
Yeah, supersonic is probably the last place you would use hydrogen because of its increased volume. And supersonically, you have volume-dependent drag, which you don't have subsonically. And so I would think that these low-speed airplanes, like the unmanned air vehicles, are the first opportunities for the use of that. But we see from these results that its impact for environmentally friendly airplanes is not so clear. Yeah.
Did you collect any interesting climate data on cirrus cloud formation after 9/11 when the planes weren't flying for 3 days?
Yeah, there was actually, that's what people cite all the time as being a significant data point, because it wasn't clear whether this was straight contrail formation or cirrus cloud formation, but whatever it was, there was a measurable change in temperature after 9/11.
It actually went down because there
Yes.
was less reflection
Yes.
from the
Yeah.
house.
Whether that was, the uncertainty of that, whether that was a single point that happened to lie here rather than on the mean, it's very iffy, but it was tantalizing data.
Well, maybe we could have a no-fly day once a year.
Yeah, that's right. Way in the back, yeah.
So I can understand sort of the reason why a lot of companies are sort of hesitant to invest in like a blended new body design aircraft. But in terms of like the performance and results, do they seem really attractive?
Yeah, they look like 25% fuel savings by going to that configuration as opposed to a conventional airplane with the very same technology. Same engines, same stability augmentation. The best estimates right now are 25% savings. So that's the carrot. The reason that you might not want to do that is because airplane companies are tremendously conservative. It costs much less to develop a derivative airplane than a new airplane, and much less to develop a new airplane that's based on your old technology than to develop a completely new method of building the airplane and having some risks associated with this. So if you're going to risk $20 billion in the company, which is about what we're talking about, you better have the probability of failure be pretty low, or you will be kicked out as CEO. Yeah.
Just out of interest, what's the overall efficiency of a jet fuel engine, say like the 767?
The new technology engines that will go on the 787, GEnx engines, and similar engines by Rolls and Pratt are about 40% efficient. Total from the fuel to the thrust.
We should probably wrap it up.
Okay.
Thanks once again.